Alright, this is Mr. McMurray again, and we're talking about elements of chemistry, and basically elements of everything in the world. Alright, so we're going to talk a little bit about elements. We kind of talked a little bit about the atom in chapter 15. Now we're going to kind of rehash a little bit of that and talk about the periodic table and why it's an important thing, and it is our friend and not our enemy. A lot of people think, oh, no, it's the periodic table, and run flying away, but keep in mind, it is your friend. Periodic tables are friends. Alright, now, first thing, let's talk about atoms. We have a bunch of atoms. If we just have atoms floating around all over the place, individual atoms, there's not much to that. We have hydrogen atoms and carbon atoms and chlorine atoms and so forth. There are about 90 to 92 elements that occur naturally and they're found, and everything in the world is made out of those 90 ingredients. But if all you had were those elements, elements being substances that are made of one kind of atom, then you couldn't make much. You had to make 90 different things. That's it. And they would just be solids, liquids, gases. They could not combine to make all the interesting things that things do in our lives. So that would be it. There would just be elements, and that's it. So in order to react with other things, they have to have a charge. And so we talked about neutral atoms. For example, we said carbon is element number 6, and we know that if it's element number 6, then it would have 6 protons. Okay, and it would also have electrons. 1, 2. Okay, and then there would be how many on the last layer? Next layer. 1, 2, 3, 4. That's horrible. Okay, but I'm not somewhere I can write on it. So there we go. And this would be a neutral atom. Okay, and this is how we started to draw atoms. But if they stayed neutral all the time, then they would not be very useful to us, because neutral atoms cannot combine. You take two neutral atoms together and they just fall back apart again. So in order to stick them together, we have to have charges. Okay, and once we have charges, and we'll talk more about how they get charges later, once they have positive or negative charges, then we can start sticking them together and make more than one atom. Now, it is possible to stick two atoms of the same element together. For example, oxygen that we breathe is O2. So it is a molecule of oxygen. A molecule just means more than one atom. But the key thing is how many elements are in O2? Still, just oxygen. All right. So even though O2, we usually do a little subscript so there's two atoms of oxygen. Even though O2 is a still one element, it is a molecule because there's more than one atom. All right. Now, on the other hand, were we to take water, which is H2O, okay, this would once again be a molecule because there's more than one atom. You actually have two hydrogens and one oxygen. So it is a molecule, but it would also be considered a compound. Okay, and so elements are important because that's what everything is made out of, but they really become more useful when we combine them to make all the millions and billions of substances that there are in the world that make this world the fascinating place that it is. All right, and so we'll talk more about elements first, and then we'll talk more about how we can use them to make compounds and how they react to do that. Okay, but keep in mind when we say molecule, it just means more than one. Now, anytime you have more than one atom held together, there are forces that help hold them together, and these are usually electrical forces. Okay, once again, and we call these forces that hold them together intermolecular. In other words, inter means between, so intermolecular forces are just forces between molecules, okay, and they hold the molecules together. Now, the tighter or stronger these forces are, the better they are held together. And substances that have very high or strong intermolecular forces that hold them together have very high boiling points, okay, and melting points, because in order for them to start moving more, it's harder for them to tear apart. Other substances that have fairly weak forces holding them together come apart fairly easy and at low temperatures and at low melting or boiling points. Okay, so for example, if you look in the room, substances that are gases at room temperature are ones that have weak intermolecular forces. Not only are they melted, but they have already boiled and become a gas. Okay, and so they have relatively weak ones. Things that are solid at room temperature, the desk, the iron and the legs of the desk, and all these things, those have strong intermolecular forces. Okay, and so basically that's largely what determines whether something boils and melts at low temperatures, or if you have to go to very, very high temperatures to make that happen. But those are the forces that hold the molecules together. Now, the other thing we need to know about molecules is that in atoms, we've talked a bit before, at least last semester, about the kinetic theory of matter. Kinetic means moving. Okay, so we know it has something to do with moving. And basically, the kinetic theory of matter is that all atoms and molecules the atoms of those molecules are moving at all times, whether it be a solid or whether it be a liquid or a gas. If we start with solids, solids are the ones that move the least. Okay, if we look at a solid microscopically, keep in mind we have no microscopes that are actually strong enough to let us see them. But one, you would see that all the atoms are tightly packed together. There's no room, and there's no basically room for them to move. Okay, so it says, but you said all substances move. Well, they move, but they can just barely vibrate in place. That's about all they can do. So they vibrate in place, and that's why they stay the same shape. And they don't move around, they don't melt, they don't flow, they don't do those sort of things because they are solids, okay? But even there, those atoms in there are vibrating back and forth very certainly, okay? And that's about all the movement they can do. Now, as you start to heat those, we know that when things get hotter, do they move faster or slower? And it turns out they go faster. As they are vibrating faster and faster, eventually they're going to get enough energy where they break loose. Okay, and when they do that, then they are coming up to a liquid. Okay, a liquid are not quite as close together. There's little spaces between them, and the molecules can start moving around. This molecule could come around and go somewhere else. Okay, and they can move around. Now they can't move outside the liquid. They're still part of the liquid. They have to move around inside the liquid, but they can move around and are much more freer to move around. Now, once again, if you keep heating them, they will move faster and faster, boiling water, as well as some of it boils and turns to gas. You have the air bubbles moving through it, but the water begins to move faster because the atoms in it and molecules in it are moving faster as well. But eventually they move fast enough that they break loose. Okay, if something evaporates like water out of a dish, only a few atoms can do that at a time, so gradually it evaporates, and eventually your dog's water dish outside, for example, could become empty because they evaporate. But it doesn't happen very fast, and all the atoms don't. If you boil it, you get it really hot real fast. All the atoms, liquid atoms, are going really, really fast, and they begin breaking loose. And now they're a gas. In a gas, the atoms are very far apart. That's why you can kind of see through a liquid a lot of times, but you can't see through. You can see through a gas, but you can't see through a solid. Why? Because of how close together or far apart the atoms are. So in a gas, the atoms are very far apart, and they're constantly moving. They're constantly moving around, boom, 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 bouncing off of things. And on the inside, that's what keeps a balloon aired up, is all those molecules bouncing around on the inside, hitting against the walls of that balloon. Okay, and so that's basically solid, liquid, and gas. Now, if you change from those different phases, from solid, liquid to gas, all right, then there's names for that. Okay, going from a solid, and then when they start moving about inside the liquid, it would be considered melting. If you're doing the opposite direction, if you have a liquid and you get it colder, and the atoms move less, eventually they solidify or freeze. Okay, and so freezing would just be the opposite of melting. All right, so if someone talks about, for example, in water, what's the freezing point of water or what's the melting point of water? Technically, it's the same temperature. It's just a matter if you're going from cold or solid, like ice, you hit the melting point, you begin to melt. But if you have water and it cools down to that same temperature, 32 degrees Fahrenheit, 0 degrees Celsius, then it begins to freeze. So it's the at that temperature, it either begins to melt or freeze depending which phase it's in and which way it's going, if it's losing energy or gaining energy at that point. All right, now if you go to liquid, eventually a liquid reaches the point where it goes fast enough, it breaks loose and becomes a gas. We call that evaporation, but keep in mind it's also called boiling. I would write that down if I were you. Boiling is when you get the entire liquid to that temperature where it can all change into a gas. All right, and if a gas can change back, for example, if you have a cold glass of water and it cools the air around it next to the cold water because the heat from the air goes into the cold glass of water, and water droplets in the air that were gases, okay, the humidity, we talk about water vapor in the air, that water vapor changes back to a liquid. And so basically you have some pure water forming on the outside of the cup and possibly running down the side, making a nice little ring on your mother's nice oak furniture, which means you're going to get in a lot of trouble, but that's a different thing. But condensation, okay, when it condenses, when you go out in the morning and there's dew on the grass, colder temperatures have caused the water vapor in the air to form water droplets, and that's what condensation is. All right, now there's one that's not on here, but basically this is going this direction. You have a solid, it would melt when it reaches high enough temperature into a liquid, which would eventually hit high enough temperature, and it would evaporate after it gains enough heat or energy and turn into a gas. In the opposite direction, if you take gas, like water vapor in the air, you lower the temperature, lower the amount of energy or heat, and it condenses into a liquid, and then the liquid would freeze into a solid. Now it's possible for things to go from one end to the opposite end without ever going through the liquid part in the middle. For example, dry ice is called dry ice because it's a solid, but as it warms up, it goes straight to a gas and never becomes a liquid. Hence, there's no wetness to it, no liquid phase. So it goes straight from a solid straight to a gas, and that is called sublimation. Now, the opposite can happen. If something goes from a gas and becomes a solid, then that is known as deposition. Okay, this is actually a fairly common phenomenon. All right. Deposition is, for example, if water vapor in the air, instead of coming to a liquid, turns directly into ice, then that is frost, or if it's up in the air, it forms a snowflake. So both frost and a snowflake, the frost in your freezer compartment of your refrigerator, is an example of deposition. Okay, sublimation, on the other hand, is when it goes from a solid straight into a gas. And if you live up north where the temperature outside never gets above freezing, you will still notice that over time the snow drifts get smaller and smaller. That's because the snow is going directly from ice, solid, directly into the air as water vapor. Okay, and that would be an example of sublimation, just like the dry ice that we mentioned earlier. So a solid, liquid, and gas are known as the three phases, or sometimes you may hear called the three states of matter. Okay, and basically as they change from one to the other, there's some general trends. In other words, if you go from solids and then to liquids and then to gases, basically the volume increases because the atoms are spreading apart and moving farther, and so they do it. Also, the ability to compress them then increases. So in other words, solids, if you try to squeeze a solid into less space, it's pretty much as much space as it can take up. But if you take a liquid, it can only squeeze a little bit, but gases can be squeezed a whole bunch into a lot smaller spaces. So they become more compressible as you go from solids up to gases. Solids are not very compressible, and then they become more compressible. Now, the density tends to decrease as you go from solid to gases. As they spread out, they take up a bigger volume, and so solids are the most dense, liquids would be the next, and evaporation or gases would be the least dense. Now, there are some exceptions to that. Water is one exception to that. As it gets down to about 4 degrees, it becomes more dense and dense as it gets colder, just like everything else does. But as it goes into the solid state, it begins to form crystals, which push it apart and make it take up more space. And so ice takes up more space than water does, which makes it have more volume, and therefore it's less dense. There's a few other elements that do that, but in general, those are the exceptions to the rule. Generally, as you go from gas to liquid to solid, it becomes more and more dense, and as you go the other direction, the density would decrease. All right. Alright, now the last thing we want to talk about, and actually we'll probably not have time to finish it, but on the next video we'll talk about the heat of fusion. In other words, how much heat does it take to get over from solid into liquid, and then also heat of vaporation, which how much heat does it take to go from liquid to a gas. But that's what we'll start up on the next video.